So, we are looking at the properties of the DFT, and the last property is Parseval's. And this is quite easy to show, and the property states the sum of the squares of the absolute value in the time domain is related to the sum of the squares of the DFT values like this, and the proof is pretty simple. If you consider 1 over n x Hermitian x, this after all is the inner product on the right hand side, and this is nothing but 1 over n cap x after all is the DFT matrix times the data vector, and hence x Hermitian x can be written like this, and from simple linear algebra Wx whole Hermitian is x Hermitian W Hermitian times W times this, and this turns out to be x Hermitian x because W Hermitian W is n times the identity matrix. Remember, W is the DFT matrix, and it is made up of columns which have the form e to the j 2 pi k n by, and these vectors are orthogonal. Actually, the implication of this is the DFT is a norm preserving transform, because this after all is the norm of the signal or the vector in the time domain, and this is the norm of the vector in the frequency domain, and all it says is, at least in this form, the norm in the time domain is a scaled version of the norm in the frequency domain. However, what you can do is you can redefine your DFT by splitting this 1 over n which was there in the inverse transform. You can split this factor as 1 over root n in the forward transform and 1 over root n in the inverse transform. If you slightly redefine the DFT by splitting this 1 over n as 1 over root n in the forward and the inverse transforms, then this norm will exactly be equal without this scale factor. So, the norm in the time domain will exactly be equal to the norm in the frequency domain. And if you redefine your DFT matrix like that, then W Hermitian W will just be I, and such matrices are called unitary. Such matrices are called unitary, and the DFT is a unitary transform. It is norm preserving. One of the interpretations that you can make of the DFT coefficients are the vector cap x, which is W times little x. You can think of this in general, if you have a vector and then pre-multiply it by a matrix A, what is the interpretation of A times x, where x is a vector? If you have an n by 1 vector little x, and if you pre-multiply it by an n by n matrix cap A, what is the interpretation of A times x? Not necessarily projection. You can think of it as, the easiest way to visualize this in the 2D case. Yeah, so geometrically what's the interpretation of the linear transformation? If you have a 2 by 1 vector and then pre-multiplied by a 2 by 2 matrix, it will be, you will get another 2 by 1 vector, right? So in general, how can you interpret this geometrically? It will be, in general, very good, rotation and scaling. If the matrix were unitary, then there is no scaling, it is mere rotation. So such matrices preserve the norm of the vector, because we are just rotating, the norm of the vector is unchanged. So the DFT is an example of a unitary transformation, and so too is the continuous time Fourier transform. So these are norm preserving transforms, and the DTFT also. If you recall the Parseval's relationship in the DTFT case, again you can split that 1 over 2 pi scale factor which was there in the inverse transform, you can split it as 1 over root 2 pi in the forward and inverse transform, and in which case it will be exactly norm preserving.